Has been important in my mathematical career back from the time when I was a student in CMI. That was around 20 years ago. So I used to meet him regularly, read with him and lecture to him. And after I returned about 7 years ago to Chennai, I continued this. Almost every week I came, I think, last 7 years, except in holidays. And in these interactions with him, I grew as a mathematician and learned a lot from him. So I'm very happy to speak in his conference. Okay, so let me start. The topic of my talk is Seshadri constant. So let me start with something that motivated this. So let's say X is a projective variety and L is a line bundle on X. Very soon I will work with complex varieties, but in the beginning that's not needed. So then we know some criteria for when L is ample. So the famous one is the Nakai-Moshe-John criterion, which says that if L meets all subvarieties of all dimensions positively, then L is ample. So using this, one can certainly, so suppose, so let's look at the following. So fix so let X be a point of X, and then I look at this ratio. So where C is a curve. So C is a curve on the variety, and we look at this rational number. Numerator is the intersection number of the bundle with the curve. Denominator is the multiplicity, so we'll assume that X is a point on the curve, so that this is non-zero, this is a positive number. So we know that if L is ample, for example, these numbers are all positive because L dot C is positive. That's an easy consequence of L, ampleness of L. But there's no reason to a priori think that the infimum of these numbers as you vary points and curves is also positive. Okay, so the Seshadri criterion for ampleness. So let me also say that in fact to show that the infimum is also positive when L is ample is easy. Okay, so that's not difficult, that's not part of the criterion, because if L is very ample, this number is at least 1 always. So if L is ample, some multiple is very ample, so this will be at least 1 over that multiple. So the positivity of this infimum is not difficult. But the criterion says that if this infimum is positive, then L is ample. So the Seshadri criterion for ampleness says that L is ample if and only if there exists, so for all X, there exists a positive real number, let's say epsilon X, such that for all C containing X. So the ampleness can be deduced from this statement. That's the Seshadri criterion. And the proof of it is using the Nakai criterion and blowing up the point and using some ampleness of the strict transform minus a suitable multiple of the exceptional curve. So it's not, I don't want to spend time on the proof of this, but this is the Seshadri criterion. So this is, I don't know exactly when, but it's in 60s. So this positive real number, of course, does not depend on the curve. That is the point. Using this, so now that we know that this happens for an ample line bundle, we can ask what is this infimum, and that is called the Seshadri constant of L at X. So using this, or motivated by this, lemma E defined so this is in around 1990, and this notation for this is, okay, so I'll often omit X, but X is the variety, L is the bundle, small x is the point. This is the infimum so you vary over curves. You can in fact vary over integral curves, because this numerator and denominator can be computed just for the components of a curve. So you can take the infimum for irreducible and reduced curves, that will give you the same infimum. And Seshadri criterion now simply can be said in the following way: L is ample if and only if Seshadri constant is positive at every point. And there is another alternate characterization of this which is also useful, and it is this. So you take the supremum. So let's say I blow up the point. So this is the blow up of x, small x. This is the map pi. And let's say E is the exceptional divisor. So then I consider the supremum of these numbers. So I pull back L and I take some multiple of the exceptional divisor. I want it to be nef. This being nef for a positive t is related to L meeting the corresponding curve positively below. Okay, so that's what comes out of usual formula for the strict transform of a curve passing through that point. So this is the same number, supremum of such things or infimum of these ratios. And this version of it is used in the proof of Seshadri criterion. Okay, so this is the Seshadri criterion, so Seshadri constant. And a quick word about why lemma E, or at least one of the reasons why he defined this or thought about this. So there is a famous conjecture which is open as of today in general, called Fujita conjecture. Okay, so X and X projective variety, L ample. Then it says that it predicts that the canonical plus ML is base point free, and let's say dimension of X is n. For M at least n plus 2. And K plus ML is very ample, so VA very ample for, this is I think 1. So this is about adjoint line bundles. So this is a famous conjecture which is proved when X is a surface. So this is a theorem of Ryder. And in higher dimension, n equal to 3, this statement is known. Ein Lazarsfeld have proved it, but in general it is open. So this conjecture is related to why Demai thought about this for the following reason. So he proved, and this itself is not difficult to show. So in the same setup, X and L as here. So I'm omitting X. X is the underlying variety. If this is greater than n over m for all x, then K plus is base point free. Okay, so this statement is the reason why he, and if it is greater than 2n over m, then it's very ample. So his approach perhaps is to prove some bounds on Seshadri constants and maybe attack Fujita that way. So if they are big, they are positive, we know, but they are in fact, there is a bound like this, then we can get this. And the proof of this is not difficult, because base point freeness and variampleness is about checking some surjectivity of some section maps with ideal sheaves. So you can blow up and make this a statement about surjectivity of some multiplication maps of line bundles, hence some H1 vanishing statement. And Codera vanishing will be used along with this statement that, something like this is Nef. If Seshadri constant, because interior of Nef cone is the ample cone, for anything slightly less than the supremum, this will in fact be ample. So that's what this Kx plus what the H1 vanishing that needs to be proved will appear like K plus something which will be ample because of this assumption. And H1 vanishing will follow and you get the base point. So this is a fairly straightforward observation. I think this was what people say is this is one of the motivations for him to define this. However, it turns out that Seshadri, so this approach broke down because the Seshadri constants can be arbitrarily small. So you can't hope for such a thing. So even though the surface case, this Fujita conjecture has been proved, it turns out that Seshadri constants can be very small. In a minute I'll tell you what I mean by this, but very small, arbitrarily small in fact, that you can't prove such a thing for all x. So this approach is not going to work. So it turned out that his original idea was not useful, but still the notion of Seshadri constants was independently interesting and people started studying it. And now in the last 10-15 years there is a lot of, maybe more, 20 years, there's a lot of work on this. So this is a very active area of research today. Okay, so in fact what I here mean by this is Miranda gave an example to show the following. So given any positive real number, there exists a triple. So here X is a surface. So two-dimensional projective variety, L is ample. Such that the Seshadri constant is less than that given number. So they can be arbitrarily small while never being. So here of course you have to, given a delta, he constructs a surface. And this in fact is a rational surface. The way he constructs this, he constructs it by a blow up of P2. So how do you get something like this? The construction is not difficult. Let me not say in detail, but just a couple of sentences. To get something like this, so we are given a delta. So if you can show that that happens, then you are done, because Seshadri constant is the infimum of such things. So you want to construct L, C and X so that such a thing like happens. So you can always take a curve with, so choose a natural number So the goal would be to construct a curve, delta, correct. The goal would be to construct a triple so that the degree of L with respect to C is 1, for example, but C has a high multiplicity point. What he does is he takes a plane curve with a point of high multiplicity. You can always, of course, choose to do that. Then he chooses another curve which meets this transversally, and he blows up the intersection points. The point of multiplicity M is not one of those, because these two curves meet transversally in this large number of points. So when you blow up, you have a strict transform of the starting curve, and he constructs cleverly a suitable line bundle, and this strict transform will continue to have this point of multiplicity m, because we have not blown up that point. Okay, so that's how he chooses this. So if you look at the construction, it seems it's very natural to do, but he came up with this idea. So this was this sort, perhaps till that point people thought maybe there is some chance of using this, but after this it was clear that this is not, that approach is not useful. So anyway, I won't continue this thought, but that's how Miranda constructed his example. So the goal of Seshadri constants have been studied in various contexts, and there are lots of questions about them. The one that I'm primarily interested in is putting them, which is often very difficult, and if you can't compute them, give bounds on them. So something like this. So can we give a lower bound? Can we give an upper bound? So the question is to bound them. So certain one bound that comes naturally is the following. So we always have the following. So this is the nth root of the top self-intersection of L, and this is immediate from the alternate characterization of Seshadri constants that I erased, because it's in supremum of some number such that pi upper star L minus T times the exceptional divisor is nef. So wherever the supremum is achieved, that will be a nef divisor, hence its top self-intersection will be non-negative, and when you rewrite those terms, it will come out this way. So what we have is these two inequalities. So they are positive and they are bounded above by that. So one considers two important cases of these. So of course remember that these are varying as you vary x. And as this example of Miranda that I didn't discuss in detail suggests, that he needed to construct a point which is pretty special in some sense, because it's a point of high multiplicity on a curve below. So the Seshadri constant for a fixed L varies a lot depending on where the point is. It can be low if the point is special. That is the takeaway from Miranda's example. But maybe it is big if the point is general. So to understand this, let's define the following. So let's define epsilon L1 to be supremum as x varies. One here refers to the fact that we are looking at one point. One can also look at Seshadri constants at R points in general. They are called multi-point Seshadri constants that I for now will not define. So you vary the points and consider this. Because of this bound, this is a bounded collection of real numbers, so it has a supremum, which is also less than this, less than or equal to this. At the other end, we define epsilon L to be the infimum. So you vary the points, look at the largest Seshadri constant and look at the smallest Seshadri constant. And these are the notations for this, epsilon L1 and epsilon L. And Miranda's example shows, and other examples show, that epsilon L can be very small, arbitrarily small, on even surfaces. It cannot be 0, so that is also, that's not difficult to show. It cannot be 0 because it will always be bounded by, if L is very ample, for example, it's always at least 1. Okay, so what I should write here is, if L is very ample, this is an easy observation, because what is this? This is the infimum of ratios L dot C divided by multiplicity. If L is a very ample line bundle, you can embed the variety in a projective space using L, L dot C is simply the degree of some curve, and below that is the multiplicity of that curve. So degree is always at least the multiplicity. So all the ratios are at least 1, so this is at least 1. Now if ML is very ample, this will come out because the numerator is just L dot C, ML dot C is M times L dot C. So now we are working with ample line bundles. So that means there is a number M which says that ML is very ample. So this is always at least 1 over M. In particular, epsilon L is at least 1 over M. Okay. But still one can ask a question. Finally, the third definition there. So these are easy facts. So the third definition is epsilon X for a variety which you define to be infimum as you vary ample line bundles on X. And this can happen to be 0 perhaps. So the question is open question. Okay, so as you vary ample line bundles on a fixed variety, is it possible that the infimum becomes 0? This is open as of now. Okay, so sorry? Blow up, you said? It's not clear. So, what line bundle on the blow up? Yeah, it may not be ample. So, even if it's ample, I don't know if there is a. Yes, it's not there, correct. So, if it's not ample, then it will become 0. Yeah. I mean, if you blow up P2, I mean, the pullback of O1 is not ample anymore, and hence its Seshadri constant would be 0. It is nef, it will remain nef. So Seshadri constant is non-negative, but it is 0 because it's not ample. But when it is ample, I don't know what one can say. There is no well understood relation between these two. So, okay, so just to recap, this can be very small. But what about this? So in a fundamental paper, Ein and Lazarsfeld, and this is 93, showed that when X is a surface, so this is important to assume now, okay, so they showed that Miranda's example came later, I think, or around the same time. I think they mention it in their paper. While the Seshadri constant can be very small at special points, or some points, let's say, the largest one has to be at least 1. This is a very strong statement. In fact, they show that, more precisely, they show that epsilon Lx, so the important thing here to remember is its surface. So epsilon Lx is greater than 1 for all but countably many points. So for all but countably many points, small x, epsilon Lx is at least 1. And so at some point just before this, I have started looking at only complex varieties. That's important for them. So that happened, let's say, here. So assume that we are working over complex numbers from now on. So for outside a countable set, this is at least one. It's become common now to call this a very general point. So a very general point is something that's outside a countable union of closed sets. Okay, so in the case, so it's such a thing would be a very general point. So how do they show this? So I will give you one basic idea because that's useful. One of the techniques that people now use in working with Seshadri constants. Yes, so this has nothing to do because you need a bound for all points for Fujita. So this is somewhat tangential to that. It's of independent interest, not with regard to Fujita conjecture, because this is only saying for a large set of points, not for all points. In order to prove Fujita, you need a statement for all points. And you don't need one because it's n by m. M is n plus 1 or something. So, but still that doesn't work because of Miranda. Okay, so the basic idea is that they show that if C, so when can this happen? If suppose this happens, what does this mean? This means that there exists a curve C containing x such that L dot C divided by multiplicity, because this number is the infimum of such numbers. If the infimum is strictly less than 1, one of those numbers must be strictly less than 1. So there is this curve C for which this happens. And now if this happens for uncountably, so it happens for a lot of points, they prove that they show that if x is very general, I don't want to get into this. In their notion, it means that there is a one parameter family of curves and points. So Ct comma xt, which satisfy this property, where small t varies over a curve. If that happens, and such a thing happens, then so c squared, so they are on a curve. So where m is the multiplicity. So they show this. This is an important inequality for curves passing through very general points. Okay. So, and this they do using some deformation theory techniques, working with a one parameter family of curves which have this property. So they proved this. If C is a curve passing through a very general point, then with this condition, then this happens. But now let's see what this leads us to. So we have m times m minus 1 is less than or equal to c squared, which is less than or equal to c squared times L squared, because L squared is positive, L is an ample line bundle. Now this by Hodge index theorem is less than or equal to c dot L whole squared. Right, that is exactly the Hodge index theorem. And now this is less than m, L dot C is less than m. So this is less than m squared, less than or equal to m squared. So you have m times m minus 1 is less than or equal to m squared. This can happen only if m is 1. If m times m minus 1 is less than or equal to m squared, m is 1. But then we have a problem. So sorry. What did I show here? Sorry, this is actually not correct. So this is m minus 1. See, because c dot L is less than m. So c dot L is less than or equal to m minus 1 squared. Now we can say that m is 1. But then that's also a contradiction, because if m is 1, that means L dot C is less than 1. L dot C is an integer, less than 1 means L dot C is 0. that is not possible because L is ample. So this cannot happen in a family. So once it cannot happen in a family, there is a countable collection of, so you look at curves which have this property, it will be a countable union of some quasi-projective varieties. So it will have countably many components, each of them discrete, so there is only countably many points this can happen. So these are two ends of the spectrum. Miranda's example gives you an example where this can be very small. Hein-Lazarsfeld say on a surface that this can't be very small. Okay. Okay, so the questions I wanted to mention, one was the one I wrote earlier. Okay, so let me just mention also this. Oguso showed that I erased just now, but epsilon L1, remember, is the supremum of epsilon Lx as x varies over small x. So there exists no, so that you can't, that will be unbounded, because certainly, yeah, you are varying, yeah, even on P2 you can. Okay, so this is I defined epsilon L1 as a supremum of some numbers, but in fact it is a maximum. That is what he proved. Not only is it a maximum, but in fact x comes from a very general set. So it's outside a countable union of closed subsets. And at the other end of the spectrum, epsilon L is also achieved. The infimum is also achieved at some points. And they have to be special in the sense that they can't be very general like this. Okay, so this is so now I'll write the inequalities somewhere I have here. So just to keep in mind, we have epsilon L is positive, it's greater than 0, which is less than equal to epsilon Lx for all x, which is less than or equal to epsilon L1, which is less than or equal to this. So this is true for all x. Okay, so there are two contrasting problems when one studies Seshadri constants. As you vary x, one expects that this number is very close to this, and this number will be less than this. So to illustrate this, so let me write another question, open question. Is there a triple like this? So it turns out that on a surface, so if a Seshadri constant is strictly less than the maximum possible value, it will have to be rational. So only way that this can fail to be rational is when it's equal to the maximum number, and that is what people expect happens most of the time. But there is not a known example of something like this. Okay, so another question, or let's say this is a conjecture. So I don't know if it should call. Okay, so at the largest epsilon is expected to be irrational, but the smallest epsilon is expected to be rational. So this is roughly what happens. Okay, so now let me talk about some recent results. Okay, so first I want to quickly talk about something that I did with Praveen Kumar Roy. So in this case, we looked at hyperelliptic surfaces. Okay, so what is a hyperelliptic surface? These are surfaces which have codiary dimension 0 and they have irregularity 1 and they have H2. So this is one of the items in the classification of surfaces. There are 4 kinds of codiary dimension 0 surfaces: abelian surfaces and K3 surfaces, Enrique surfaces, hyperelliptic surfaces. So this, and alternately one can characterize them by X can be written as a finite group quotient of a product of 2 elliptic curves. So A and B are elliptic curves. So G is a finite group of translations of A and G acts on, okay, so this is the assumption. So G is a finite group of translations of A, it acts on B such that B mod G is P1. So it's known that these are equivalent descriptions. If you have a surface satisfying this, you can, this is classical, this is more than 100 years ago. So we looked at such surfaces. They're useful to look at because their Néron-Severi, the ample cone and so on are well understood on this. So it turns out that the Picard rank of such surfaces is 2. So ample line bundles are understood on this, and there is a classification of them which says that there are 7 types of such surfaces. Okay, so there is some classification, I don't want to get into that. Depending on what the group is, this is Z mod 2Z, Z mod 3Z, Z mod 6Z, and the way it acts on B. So there is a classification and there are 7 such types, and so we have something to say about this question in that case. Okay, so the theorem, the first theorem here is, if L, so Seshadri constants are really defined for numerical classes of line bundles, because if 2 line bundles are numerically equivalent, they have the same as Seshadri constant. So one needs to only look at the numerical class of them. Here it is rank 2 Néron-Severi. So any line bundle can be up to numerical equivalence, be given by 2 integers, and it will be ample if both are positive. So that is the ample cone in this case. If this is ample, so then what we show is that epsilon L comma 1 is greater than or equal to 0.93 times square root L squared, or epsilon L1 is minimum okay, so let me say that A and B, which are the underlying elliptic curves, are actually fibers of the two projections. So A and B, there are isomorphic curves on X, there are curves on X which are isomorphic to A and B. So one can look at L dot A and L dot B. So this will not make a lot of sense. The way to read this is epsilon L1 is close to square root L squared. That is the way you should read this. 0.93 is close to 1. Or it is easily computed. So this need not happen, but it's easily computed. That is the way to understand this statement. One expects that epsilon L1 is very close to square root L squared and often equal to square root L squared. So it is at least, we gave a bound and said that it's within 0.93 times that. Okay, so another result in the same setup. Okay, so again, this is not, because I can't explain much here, X is not of type 6, then so as I said, there are 7 types of hyperelliptic surfaces, 1, 2, 3, 4, 5, 6, 7. If it's not 6, this is all of course just jargon right now. If it's not one of those types, then epsilon L is Q, in Q, which is related to this question here. So people expect that the least Seshadri constant is a rational number. We prove that in all but one of those types. And this is an open question which is in fact not known in most cases. It's not known. Even for blow-ups of P2, this is not known. But I don't want to spend any more time on this because I want to talk about one more result. So these are some of the results that we proved on hyperelliptic surfaces. So the last thing I want to talk about is some recent joint work with Indranil, Nagaraj and Newstead. So we look at Grassmann bundles on smooth curves. So let me give you the setup. Six, not of type 6. 6. So there are 7 types, except in one of those types we prove that result. Our proof doesn't work when it's type 6. So in this work let me say, in the paper we call it X, but to be consistent with what I'm doing here, let me call this curve C, but of course that messes up my notation for curves. Projective curve. It won't play a role, so let's just, what I want to do is look at Grassmann bundles on this curve. So we want to look at a vector bundle. E is a rank n vector bundle on C. Okay, so the object we want to study is this. So this is a variety that parameterizes so this is a more general version of or generalization of projective bundle. So this characterizes dimension R quotients of fibers of E. Okay, so this is what we want to look at. So in this setup of the talk, X is this. So the goal is to study Seshadri constants on X. Okay, so the first advertisement is, lot of work on Seshadri constants is done for surfaces because it's already difficult there. Then there are lots of open questions and people have spent a lot of time on surfaces. And very little is known in higher dimensional varieties. So this is one such example. So where we have some statements for Seshadri constants on higher dimensional varieties. This will be you can compute the dimension of this, but it's certainly not a surface in general. Okay, so we want to study on X, and only situation where people have studied this is when actually you have a rank 2 vector bundle and you look at the projective bundle of it, giving you a ruled surface. So as I said, a lot of work has been done on surfaces. One of those is the case of ruled surface. So our setup includes that. So we obviously, whatever we prove should cover those results that people should know for ruled surfaces. So ruled surface is a special case of this situation. Okay, so now we want to choose R suitably. So Grassmann bundle of parametrizing. So how to write this? R dimensional quotients of fibers of E. So R is to be determined. So what is R? So we look at the Harder-Narasimhan filtration of Harder-Narasimhan filtration. It looks something like this. So what we do is let M be something between 1 and D, between 2 and D, and let R be the rank of. Okay, so this is how we set it up. So we take, so it's the rank of tail of this filtration. So E mod somewhere in the middle. Yes, so yes, it's not semi-stable, yeah. Yes, so that is the first assumption. So if E is semi-stable, then E m minus 1. So E modulo something in the middle. Now if E is semi-stable, then of course this is just N. I mean, you can take either 0 or E, right? That's the filtration. So you don't get anything. So we certainly want to assume that E is not semi-stable. Sorry? No, that we are not assuming. So look at the Grassmann bundle for this R. So that is the variety that we consider. Okay, so the starting point for us was a result of Indranil and Parmo. So the Neff cone, so the same setup. So we have E, R defined like this, M is anything. So we get different R's for different M. So fix some M and hence fix some R. So Neff cone of this is generated by or spanned by so these are Picard rank 2 varieties, and the Neff cone is generated by this. What are these L and M? Where L is the class of a fiber. So f is the, let's say we have x to C, that's the morphism. So a fiber will be a divisor, so the corresponding line bundle is the L, that's L, and M is O1, so x is this, OX1 minus theta times L, where theta is the degree. Where theta is the degree of this quotient, whose rank was R. So E mod, this whatever we picked here, that rank is R and that degree is theta. So they showed that the Neff cone is generated by these two. So Neff cone is a cone with extremal rays coming from these two. So now whenever we try to look at Seshadri constants, this is a good starting point, because this tells us what ample line bundles are. And once we know Neff cone, its dual is the cone of curves. So that also can be computed using this. So that's a good starting point, because we know what are ample line bundles and what are curves. So we started from this point, and using this result we wanted to compute what Seshadri constants are on X. Okay, so and in order to do that, let us identify some curves on this variety X. So the first one is, so define gamma L to be class of a line in a fiber of F. So a fiber of F is a Grassmannian variety. So we take a line in that. So that's just a generator of its Picard group. So that, or the Neff cone of curves. So we take a line. So that's a curve in the variety X. And similarly, we take gamma S, gamma sub small s, to be image of the section So the sections of this Grassmann bundle correspond to rank R quotients of vector bundle E. Okay, this is analogous to what happens when you take projective bundle. Their sections come from line quotients. So here there are rank R quotients. And we have a fixed special quotient, E mod EM minus 1, which is what we have fixed a priori. So that particular quotient gives you a section. So that image is a curve, so which I am calling gamma S. So a simple, some investigation of the intersection of intersection pairing on this variety X, in particular how L and M intersect gamma L and gamma X, tells us that gamma L and gamma X actually span the closed cone of curves. Gamma L and gamma S span NEX, the closed cone of curves. Okay, because this is dual to the Neff cone, and L and M have L with this has intersection 0, L with this has intersection 1, and M has a similar property. So they span the cone of curves. This is the dual cone. So with this data we can use we can do some computations. So we have two results making a couple of assumptions on those filtrations, further assumptions. But before stating them, let me just quickly try to illustrate how to compute Seshadri constants on this Grassmann bundle. We use that to get the, so far, except to define R, it did not look like it's needed. But we use it in the main results, yeah. Okay, so I will illustrate how to compute this, but let's say L be a ample line bundle. Because the Neff cone is that, so L can be written as, or at least numerically equivalent to something like this. Okay, and A and B are positive integers. So any ample line bundle is of numerically like this. And we need to only compute Seshadri constants up to numerical equivalence. So let us take this. So we want to compute the Seshadri constant of such an L at some point of x, and so let me use the letter D. D be a curve containing x, small x. So D is a curve on the Grassmann variety containing the fixed point small x. So we are interested in this ratio. We are interested in this ratio. So there are a couple of cases. So let me consider these cases. So case 1 is that suppose D is contained in a fiber of F. F is the structure map from the Grassmann variety to the curve. Suppose D is contained in a fiber, but the fiber is a Grassmannian variety. So in the cone of curves, D will be written as, so I guess I can write it like this, NL, because gamma L is a class of a line in the fiber. It's a curve, so it must be something like this, where NL is, so I can assume it's a actual curve. So NL is some positive integer. So this allows me to compute the Seshadri, the intersections. So I'll finish in maximum 5 minutes. So I think I have 2 minutes, correct? Okay. So then what is L dot D? So this is LA. Okay, so I'm going to be, it turns out that, so I should write that here just for, so this is the intersection on the variety. That's why these span the cone of curves, because this is exactly the dual basis. So using that, we get that this is BNL. Okay, so that is just the additivity of intersection. D is NL gamma L. This times gamma L is 0, so this times gamma L is B times NL. Okay, and another point is see D is a curve in the Grassmannian variety, so it's a degree NL curve. So if it has a multiplicity, whatever its multiplicity is, it is bounded by the degree. So multiplicity is less than or equal to NL. Okay, so together these two facts imply that L dot D divided by multiplicity of D at X. So this is equal to BNL by BNL divided by multiplicity. But NL is greater than or equal to this, so this is greater than B. So really, without doing anything, we have a bound on the Seshadri ratios for curves contained in the fibers. And similarly, we can do something for curves that are not contained in a fiber. So let me just take 2 minutes. So suppose D is not contained in a fiber. So this is the second case. So we write D as some NL gamma L, NS gamma S. Let Y so I have chosen a point a priori. One of the fibers of small f contains that point, so let Y be that fiber. We know that D is not contained in Y because D is not contained in fibers. So D dot Y, so D is a curve, Y is a divisor. So D dot Y I can talk about, which is of course L dots D, because Y is a fiber, L is the class of a fiber. So L dot D, so what I have here is this. So this is a Bezout's theorem statement. So you have a curve and a divisor such that the curve is not contained in the divisor. So the intersection is at least as much as the multiplicity of that curve at the divisor. So anyway, let me just wrap it up now. So using this we can multiplicity is at least A. Okay, so the similar calculation as before tells me that multiplicity is at least A, where A is this. Okay, so this is something that I can say in general without any further assumptions, but in order to say something actually useful about Seshadri constants, we need to make a further assumption on the Harder-Nasiman filtration. So let me end by writing this theorem. So we have two theorems making two different assumptions on the filtration and concluding different things about Seshadri constants. So let me maybe write one of them. Okay, so what is the assumption we want to make? So assume that mu, so this is the assumption. Okay, so this is a fairly technical inequality here, but remember that E mod EM minus 1 was R, which was the starting point of all this. So we want that slope of that particular quotient minus the previous one to be less than or equal to the degree of E mod EM minus 1. So this surely means nothing for you now, but this is what we want. L as above. So then ample. So the statement is the Seshadri constant of L at X is B if B is less than or equal to A, or X is not in gamma S. Gamma S being one of the curves that generates the cone of curves, or it is A if A is less than B and X belongs to gamma S. So last thing I'll write. So we have, so to tie it up with what I wrote earlier, I talked about epsilon L1. So epsilon L1 is B and epsilon L. Epsilon L1 is the largest Seshadri constant. That's always B, no matter how A and B are related to each other. And epsilon L is minimum of A and B. Okay, so, and the last remark is that, as I said, people have looked at Seshadri constants for ruled surfaces, which is included in this setup, because you can take a rank 2 vector bundle and look at which is not semi-stable, so that there is a Harden-Asselmann filtration and there's a line sub-bundle, and our results recover those results. So in that particular case, whatever is known is recovered under this theorem. Okay, so I'll stop here. Thank you.